Good morning, everyone. I hope you had a nice weekend. We had open day, so I didn't really have a weekend. That's why I'm drinking a coffee.
How was open day?
It was very quiet. So it was a waste of a Saturday, to be honest. Okay. Today we're going to do electrochemistry. I'm sure you're all very excited about that. I'm so excited I jumped out of bed this morning and I couldn't wait to get here to tell you all about electron transfer reactions. Now, like with the acids and bases, I'm starting from zero because, it makes no sense to start with the Nernst equation when you haven't done the basics. So, in the interest of getting everyone to the same level, let's go back to zero. Okay, now, redox reactions are reactions where we have a transfer of electrons taking place in a chemical reaction. Now, the way that we figure out whether or not electrons have been transferred is by looking at the oxidation states. And if there's been a change in the oxidation state, we know that there's been a transfer of electrons. Let's look at this example here. This is the reaction of iron oxide with carbon monoxide. Iron oxide is rust to form elemental iron and carbon dioxide. Now, how would we determine the oxidation states of the iron? Does anyone have a suggestion? No suggestions. Okay, well, oxygen, O, is in which group? Group 6. So in order for oxygen to have the octet electrons, octets to fulfill the octet rule, you see the stuff that we did in the first couple of lectures is coming back to haunt us. How many additional electrons do I require? 2, because it's in group 6, it's got 6 valence electrons. So if I add 2, it will have 8 valence electrons fulfilling the octet rule. So the oxidation state of an oxygen atom is 2 minus. Okay? Now we've got 6 of those, so in total we've got 6 minus. Iron oxide is neutral. So what would the charge of each iron atom be? If this is 6 minus in total, what is the charge per iron atom? Plus 3. So the oxidation state is plus 3, right? Plus 3. All right, and now let's look at carbon monoxide. What is the oxidation state of oxygen? 2 minus. What is the oxidation of carbon? 2 plus, because it must be balanced, right? Because the thing is not charged. So that's what we have on the left of the reaction. And on the right we have iron, just iron. What's its oxidation state? 0. Elemental, things in their elemental state have an oxidation state of 0. And what about the carbon atom here in carbon dioxide? Plus 4, because we've got 2 times 2 is minus 4, so to balance that is plus 4. So we can clearly see that we have a change in the oxidation states. Iron is going from plus 3 to 0. It's changed its oxidation state. Oxygen stays minus 2, but carbon is going from plus 2 to plus 4. So this is a redox reaction by definition. There's a change in the oxidation states. And the only way that we can change the oxidation states is by moving electrons around. So a redox reaction is a reaction involving electron transfer. Now, we can break down a redox reaction into 2 half reactions, so-called half reactions. Again, this is revision because we did this in a task, so this should all be somehow familiar to you. Anyway, I'm just repeating it for the sake of completeness. We have a so-called oxidation half reaction where we generate electrons, and we have a reduction half reaction where we pick up those electrons. And these two go hand in hand to form a reaction. Alright, now the way to remember this, oil rig, oxidation is loss, reduction is gain. Clearly in this half reaction we're losing electrons, right? You can see if we go from left to right, we're generating electrons there. This N is just, for example, if this is some metal, it goes to a charge of N plus. And of course, to balance that, we'll then generate n electrons. So that would be an oxidation half reaction. And the reduction half reaction would be something else, another metal that picks that up. Okay. Now, here we have an actual example. If we look at the redox reaction between copper, metal, and iron. In other words, if I take a piece of copper and I put it in a solution of iron sulfates, iron 3 sulfates, for example, look at what happens. The copper goes to form copper 2 plus, and it generates 2 electrons. So it's being oxidized, and those 2 electrons are then, or well, actually 3 electrons, will be picked up. So we need to balance it. We'll look at that in a minute. So in other words, the electrons that have been generated in the oxidation half reaction gets picked up in the reduction half reaction, in this case by iron 3 plus, and it forms iron 2 plus. Okay, it's picking up 1 electron, sorry. So if we look at actually what's happening here, this is copper, this is the surface of the copper, there you see it in an iron sulfate solution. Actually, the copper is generating these 2 yellow dots here are the electrons that's being generated, and it's forming an ion, which goes into solution. Those 2 electrons that are generated are then picked up, in this case by iron 3 plus, to form iron 2 plus. So that's sort of what's happening. Now, one has to balance these reactions in terms of electrons. We'll get to that in a moment. But the point is, you can't have an oxidation half reaction on its own, right? You need to have an oxidation and a reduction reaction together. The one is generating electrons and the other one is picking electrons up. Oxidation and reduction, therefore redox. Okay, now let's come back to this example that we just looked at, copper going to copper 2 plus and iron 3 plus going to iron 2 plus. What's the problem? I've written 2 half reactions here. Can someone tell me what is the problem?
The electrons don't match.
Yes, the electrons don't match. I've generated 2 here and now you require 1 here. So what's the remedy for that?
2 Fs.
We just multiply the bottom half reaction by 2. And if we do that, it balances. So what we have is and this is the process with redox reactions, you always build up half reactions, balance those, make sure that the electrons balance, right, by multiplying through by a stoichiometric coefficient throughout, like we did here, and then you basically just sum everything, and you get a so-called, this we call a net ionic equation, right? Net ionic equation or reaction. Because I've left out so-called spectator ions, right? I could have, because this is iron 3 plus, I could have added in sulfates, which are spectator ions, not really involved in the redox reaction, and you can put that in here, and then you get so-called full molecular equation, but it's not very important. For redox reactions, we just consider the species that are actually involved in the electron transfer. So that's an important point. Make sure that the electrons actually, are the same. All right. How do we proceed with the balancing? Well, you break it down into half reactions, step 1. Step 2, you balance each half reaction in terms of electrons, and in terms of atoms. So you make sure that the atoms on the left equal the atoms on the right. Then you balance in terms of charge. And the 4th step is to make sure that for each half reaction that the electrons are the same. So like we saw here. So if we look at this half reaction here, the coppers are balanced. So we just go to step 2, balance in terms of charge. So you add 2 electrons there. And step 3 is then to make sure that the electrons that I'm generating in the oxidation half reaction is the same as the electrons that I'm using up in the reduction half reaction. Are there any questions? Okay, I know it's Monday morning.
Could you explain again in step 3 how to balance charge? Really good.
Well, step 1 is to, so we confronted with the reaction. Maybe we should just do this. All right. So we have a piece of copper in a iron 3 plus solution, and I want to write a balanced redox reaction. So copper is going to go to copper 2 plus. Iron 3 plus is going to go to iron 2 plus, apparently. Now that's what we left, that's our starting point. The one is the oxidation half reaction, but we don't know which is which yet. Now that's the first thing we do is we check for each half reaction if the elements are balanced. Are they balanced? Yes, I've got one copper here, I've got one copper here, one iron here, one iron here, so I don't need to do anything. Now I balance in terms of charge. I've got a 0 charge on this side of the reaction, and I've got a 2 plus charge on that side of the reaction. How do I balance it? So that half reaction is now balanced in terms of atoms and in terms of charge. Now let's go to the iron 3 plus. What do I do, Stephanie? Correct. So now each half reaction is balanced in terms of atoms and charge. Now what's the third step is to finally do what? Chai. Correct. So I'm generating 2 electrons here. I only require 1 electron here, so I've got to multiply this by 2 so that I get that to balance. So it becomes 2 electrons plus 2 Fe3 plus forms 2 Fe2 plus, and then to get the overall, so now the 2 half reactions are balanced, and now I just put it all together and I get the net ionic equation that you see now. So that's the way to proceed for very simple redox reactions, the balancing. Okay, now this is just to show you that we have a change. I mean, this is if you sum the charges on the left and on the right, you can see that there's a change. So yeah, this is just another way of balancing it. Just looking at the overall reaction and basically counting the charge on the left and on the right. I don't really like this way of doing it because it's confusing. The best way to do it is always to break it down into half reactions. Okay? Now, let's get to the next challenging problem. Though we've now looked at redox reactions, simple redox reactions, where we just have basically electron transfer involved. Now, it could happen that we have redox reactions with species containing oxygen atoms, and then things get a little bit more complicated because then in the balancing procedure, we have to add water molecules and H pluses and stuff like that to get it to balance. Some of you might have seen this in high school. How many saw this in high school? Okay, so about a couple. Right, so let's go through this, okay? I want to balance this reaction. Now, remember when we were discussing molar calculations, how did we balance reactions? By inspection. We looked at the reaction equation, which is balanced by looking at it. We need something on this side, we need something on this side. Now, it's difficult to do that with these sorts of redox reactions, so we need a more sophisticated way of balancing it. Now, this redox reaction is difficult to balance because we've got oxygens involved. Previously, we just had metals going to metal ions. There's no oxygen involved here. But now, look what's happened. I've now got species. This is called a chlorate. This is a chlorate ion going to a chloride, and an iodine going to an iodate. Iodate, IO3. So there's oxygen in the actual species. How do we balance it? Well, for the purposes of this course, we're only going to look at balancing in acid media. You can also balance in basic media, but let's suppose this reaction is taking place in an acidic solution. What does that mean if it's acidic? What do I have a plentiful supply of? Correct, H plus, or H3O plus, whichever you prefer. So, the procedure to balance these, I've written down in a step-for-step fashion here, and I want us to do this example together. Now, it's very similar to what we just did with balancing this reaction with iron and copper, except we built in we need to build in an additional 2 steps for balancing the oxygens. So the first step, let's do it step for step, is to construct the half reactions. So let's construct the half reactions. What are the 2 half reactions going to be? Sorry?
CiO3 to Cl.
Yes. Makes sense, right? You don't need to be a rocket scientist to realize that obviously ClO3 is not going to go to IO3. I mean, you can't, it just doesn't make sense. Chloride can't suddenly become iodine. So obviously, these 2 are going to go together, that one, and the iodine and the iodate, obviously. So that's the starting point. It's very simple. We write that down. Don't forget that it's an aqueous solution. And the other one is I2 aqueous to IO3 minus. By the way, just out of interest from the Departments of Useless Information, we have, these are very interesting species. We have IO minus, IO2 minus, IO3 minus, IO4 minus. The IO minus is called hypoiodite. Hypoiodite. IO2 is iodite. IO3 is iodate. And IO4 is periodate. So a bit on the main picture. Same for chloride, which is what we have in this reaction. Just some interesting information. So what would that be? ClO is hypochlorite. Chloride, chlorate, perchlorate. I'll never forget this because this was the first lecture we had. In our very first lecture at university in chemistry, we discussed these things. It's funny what you remember. Okay. Now, let's come back to the matter at hand. So we've got the 2 half reactions. Now what's the problem? We have to balance all atoms. The first step is, for each half reaction, for each half reaction, balance all atoms other than hydrogen and oxygen. Are they balanced? Tara. For the top half reaction. Well,
Everything else?
yes. Everything other than hydrogen and oxygen, this is the next step. For the second half reaction.
No.
So how are we going to remedy that?
We need to make it H2.
Now it's balanced. The iodines are balanced. Next step.
So is the ClO3 supposed to be minus?
Oh yes, sorry. Thank you. Paying attention. Let's go. All right. What's the next step? Claudia.
Add water.
Okay. Why?
In order to balance the oxygen.
Correct. So we do that again. We're doing this 1 half reaction at a time. Okay. So just consider each half reaction. So how do we do that, Anouk?
By adding 3 H2O
Where?
on the right side.
Correct. So if I add 3 H2Os, now the oxygens are balanced. And I can do that because the reaction is taking place in an aqueous solution. There's lots of water. What about the bottom reaction? Circa, how do I remedy the oxygen problem?
3 H2O
Where?
on the right.
On the right.
Oh, sorry, left.
On the left.
So
Okay.
6, isn't it 6? Yeah.
Oh, sorry, it must be 6, yeah? 6. Yeah. Because we've added a 3 there. Don't fall into the trap like I nearly did. Okay, next step. We have to balance the hydrogens. What do we do?
Add H plus.
Where? Correct. How many do I have in total? I've got 6. So I had 6 H pluses. And I can do that because it's in an acid medium. Okay? Now what about the bottom half reaction, Stephanie?
You have to also add H plus to that side. You need 12
To which side?
to the right side.
Correct. Right, what's the next step? Now we've got notice all the atoms are balanced. All the atoms are balanced. What do we do now? Now we have to balance each half reaction in terms of electrons to balance the charge. So how do we do that? Let's start with the top half reaction. Well, on the left-hand side, we've got a total of 5 plus, 6 minus 1 is 5. So let's write that down, 5 plus. And on the right-hand side, I've got 1 minus. So what do I do?
Like 6 electrons to the reactants.
Correct. So I add 6 electrons here. Now it's balanced in terms of charge. Right, what about the bottom half reaction? On the left, I've got what charge?
0.
And on the right?
10.
So what do I do?
Add 10 electrons to that side.
10 electrons. Is that correct? No. Yes, it is correct. It is correct. So we've got 2 minuses plus 12 is 10 plus. Yeah, so now it's balanced. Everyone agree? Katarina? You following?
Yeah, I think it's, yeah.
Alright, what's the next step?
Balancing the number of electrons.
We have to balance the electrons. So if we multiply this reaction by 10 and the bottom reaction by 6, the electron count will be the same. So I'm going to write in red now what we get as stoichiometric coefficients if I do that. So if I multiply the top reaction by 10, I get 60 H pluses plus 10 ClO3 minus plus 60 electrons forms 10 Cl minus plus 30 H2O. Okay?
Wouldn't it be easier to multiply the top one with 5?
Sorry, I can't hear you. Can you speak up?
Wouldn't it be easier to multiply the top reaction by 5? And
Right. And of course, you can select another. I'm just doing it the easy way. You'll see what happens. We can simplify it at the end. All right, bottom reaction times 6. 6 times 6 is 36 H2O, 6I2. 6 times 2 is 12 iodates. 6 times 12 is 72 H pluses plus 60 electrons. And so, do you all agree with me now that basically everything is balanced for each half reaction? Atoms, electrons, charges. Now, what is the next step? We just draw a big fat line and we put it all together. Let's do that. So we write everything that's on the left. So we get 60 H plus. Just put it all down. 10 ClO3 minus plus 60 electrons plus 36 H2O plus 6 I2. I'm not being very, very good here because I must put these in. Plus 6I2 goes to form 2IO3 minus. No. See, it's easy to make a mistake here. You guys must check me. 36 H2O plus 6I2 forms 10 Cl minus plus 30 H2O plus 12 IO3 minus plus 72 H plus 60 electrons. Does everyone agree that that is the net ionic equation? Does everyone agree? What do we do now, Anouk? We can simplify things. It's like an equation. like a mathematical equation. What can we do? That cancels with that. That's good, because when you write the net reaction, there shouldn't be electrons left. Okay? And that's how you can check that you balanced it. What else can we simplify? Well, we've got 36 waters on the left and 30 on the right. So let's do this. Let's make this a 6. Right? Because if I simplify, I get that. What else can we simplify? We've got 60 H's on the left, and how many on the right? 72. So if I take that to the right, what do I get up? I get here 12 H pluses. Simplifying. Can I simplify anything else? Yes. No, I can't. I think that's it. So the net reaction of the simplification is 10 ClO3 minus aqueous plus 6H2O plus 6I2AQ goes to form 10Cl minus plus 12IO3 minus and plus 12H pluses. And what can we do now? There's one further simplification step to come back to your suggestion. We can divide all stoichiometric coefficients through by a common 2, right? And what do we end up with as a final grand solution? We'll end up with 5 divided through by 2, ClO3 minus plus 3H2Os plus 3I2 5Cl minus plus 6IO3 minus plus 6H plus. That is the final solution. That's, yeah, as you can see, if you can count it up and you can check, you should do that. That everything on the left equals everything on the balances, everything on the right. But now notice, this is not a reaction you could balance easily by inspection. That's why we need to balance these reactions using this methodology. Okay, so that's very important. Very important. Now let's soldier on and look at nomenclature. Now we did discuss this in the tutorial. It gets a bit confusing. An oxidizing agent is an agent that itself gets reduced, and a reducing agent is an agent or a species that itself gets oxidized. Makes kind of sense because the word agent means it's doing something. So an oxidizing agent is oxidizing something else, which means, per definition, it itself is being what? Reduced. And similarly, a reducing agent is an agent, a thing, not a secret agent, a chemical agent, that is reducing something else. It means, by per definition, it itself is being oxidized. Don't get confused. All right. Now we come to the very important point of so-called reduction potentials. Now, it is possible for us to measure, because we're working with a transfer of electrons, obviously there's going to be a potential associated with an electrochemical event. Okay? And of course the unit for the potentials is the volts, which is a joule per coulomb. So it's essentially work over charge, potential. Now, basically what this boils down to is if I have an electrochemical reaction taking place, I can measure the potential relative to a standard electrode. And I'm going to get a certain potential associated with it because, after all, it's electron transfer that's going on. And if it's an electron transfer reaction that's going on, obviously, there's going to be a potential associated with it. So, basically, I want to just show you what this looks like. First of all, how this works is generally we measure these potentials relative to something called an SHE, a standard hydrogen electrode. In other words, what it is it's an electrode where we have hydrogen gas coming in, in an acidic solution, there you can see the bubbles forming, a platinum electrode. And what we basically do is we attach this electrode, the standard hydrogen electrode, to a voltmeter to measure the potential. And on the other side, we have the thing that we're trying to measure the potential of. So on the left here, for example, this would measure the potential associated with the copper, with a half reaction, with the following half reaction. Let me write it down. This is important that you understand where these potentials come from. Okay. So if I want to measure the potential of this half reaction, which we just saw moments ago, the way that I would do it, the way that I would determine the potential associated with that half reaction is like I'm doing it here. Relative to a standard electrode. Everything in science is relative to something. There's no absolutes. You always have to have a standard, right? Now I could have selected another electrode. There's other standard electrodes. But generally this so-called SHE standard hydrogen electrode is the one that we use. And we report potentials relative to that. So the potential associated with this reaction, half reaction, H2 to H plus, H2 going to H plus, 2H plus plus an electron, we set at 0. That's how this whole thing works. And so relative to that we have copper. Now notice here we have like a porous plug, so it's, it's possible for things to, it's sort of like a salt bridge. Now, over here, we have another half reaction, zinc going to zinc 2 plus. We again have our standard hydrogen electrode. What do you see? What is the difference in the potentials? Start with the potential. What is the potential associated with this copper half reaction?
0.34.
Sorry?
0.34.
Yes, 0.34 plus. That means the process is going to happen. What about the zinc reaction?
It's not going to happen because
It's
it's negative.
negative. It means the way to interpret these signs is that if hydrogen is 0, if we have a positive value associated with the potential for a half reaction relative to the standard hydrogen electrode, that the likelihood of that process taking place is, well, good. And if it's negative, it's unlikely that it's going to happen, right? The more positive, the more likely the process is going to take place. The more negative, the more unlikely. And that brings us to this table over here. And this is what scientists did in a laboratory. They built the standard hydrogen electrode and measured the electrochemical potential for all of these half reactions relative to hydrogen. Notice I've circled it here, which we set at 0. So looking at that table, right, fluorine is right at the top. So this is a reaction that has a potential of 2.87 volts associated with it. It means it's very likely that it's going to happen. Another way to say it is that this is a very, very strong oxidizing agent, right? It's a strong oxidizing agent because the potential associated with this half reaction, where it is behaving as an oxidizing agent, notice it itself is being reduced, so it's an oxidizing agent, is very high. The values decrease as we go down until we get to 0, and then it goes to a minus, meaning that these processes are unlikely to occur. But lithium, where fluorine is an excellent oxidizing agent, lithium is what? Yes, lithium metal. Okay. So, the other thing I should mention about this table is that we read from left to right. Okay, in other words, the potential associated with, let's take cobalt-3 plus an electron to cobalt-2 is 1.82 plus. In other words, if cobalt-3 is reduced to cobalt-2, the potential associated with that process or electrochemical event is 1.82 volts. What is the electrochemical potential associated with the following event or the following process? What is the electrochemical potential associated with us? Minus 1.82. So that is how this table works. If you write from left to right, if the reaction appears in the table as it's, if you write down the reaction as it stands in the table, you can just use the potential that's given. If you swap that reaction around, you swap the sign of the potential. So, what? So cobalt-3 plus an electron forms cobalt-2 plus 1.82. Cobalt-2 plus going to form cobalt, so the inverse of that is minus 1.82 volts. Now this is very important. Very, very important that you understand what this table means, how to interpret it, and how to use it. And actually, I want you to forget everything that your high school chemistry teacher told you, because I'm pretty sure they told you all sorts of nonsense about E cathode minus E anode and all that stuff. All you need to do is sum potentials. It's a common problem. The way that electrochemistry is taught in high schools is it's not done in a very reasonable way. I'm generalizing now. I mean, maybe you were lucky and you had good teachers, but what they tend to do is teach tricks and like methods on how to, interpret the table rather than actually understanding what the table really means, right? Anyway, it's a generalization. It's just maybe you're lucky, but I've noticed time and again that students don't really understand what this table means and what it's telling you. All right, so how does this work? Let's soldier on. So now let's suppose, all right, this is what I've just said. This idea of, it's the tendency of that electrochemical event to take place. If it's positive, it's relative to hydrogen. It's likely that it's going to occur. If it's negative, it's unlikely. Now, we talk about, if in this table we just saw, it reflects, we call it standard reduction potentials, right, or standard electrode potential. Standard means, and this is going to be important later on in the lecture, standard means that we're measuring it at standard conditions, and in this case, we use a 1 molar concentration. We're doing it at 1 bar or 1 atmosphere pressure. Well, 1 bar is not exactly 1 atmosphere, but approximately, and we're doing it at 298 Kelvin. If we do the measurements at a different concentration, or a different pressure, different temperature, is going to affect the potential. So that's why it's important to specify these conditions. And so what I'm actually talking about is these measurements here, the measurements that I get in this table from doing this experiment in a laboratory, is done under standard conditions. 1 molar concentration copper 2 plus, 1 molar H plus, you see there, 1 bar atmosphere, not 2. There's 1 bar pressure going in here, and it's done at 298 Kelvin. If I change those conditions, I'm going to change the potential. So that's why in the table you see standard reduction potentials at 25 Celsius for many common half reactions. Yes, there's a question.
Why is it in bar and not in Pascal? Because that's in SI.
Yes, well, you're right. There's many different units for pressure. There's millimeters mercury, torr, psi, bar, atmospheres, pascals, etc. At least 6. And scientists tend to sometimes be quite sloppy. You're right, it should be in pascals, but we use bar sometimes.
Is it maybe because it's easier to measure? Is there something like
Not really, not really. I mean, you can readily convert that to pascals. In fact, what is 1 bar and how many bar are there in, how many pascals are there in 1 bar or in 1 atmosphere? 1 atmosphere is not exactly the same as 1 bar. It's close, but the conversion factor just from the Department of Useless Information, I think, is 101.2, 101 approximately. 101 kilopascals is 1 bar approximately, something like that. I think it's 101.3. So that's 101,000 pascals. So if you want to write 101,000, knock yourself out. It's easier to write 1 bar. I think there's your answer. Okay, so you all understand what this means, because it's going to be important, very important now. So, why are some potentials positive and negative? We've looked at that. We've looked at this. Now, here's another important note, and this is of paramount importance. When you're balancing the reaction like we've been doing, right, and you want the potential associated with the half reaction, you don't multiply the potential by whatever factor you've multiplied the reaction by. Remember when we balanced the reaction copper, remember when we balanced this reaction here, the copper reaction? Remember the story here, I multiplied the bottom reaction by 2. Now if I do that, I'm not going to multiply the potential, of this half reaction, which we can look at a table. Let's find it. There it is. No. Iron 3 plus, there it is. No, there it is not. Where is iron 3 plus? Ah, here. Iron 3 plus an electron forms iron 2 plus, has got a potential associated with a 0.77 volts. I've multiplied, in balancing this reaction by 2, I do not multiply the potential by 2. It's 0.77 irrespective of the stoichiometric coefficients that I've multiplied it through by for the purposes of balancing. Did everyone get that? That is a mistake that so many students make. You cannot believe. Please don't make it in this class. I'll be very sad. All right. Now, why is this important? All right, here I've just shown you again exactly. The potential stays the same irrespective of when I multiply through by this stoichiometric coefficient. All right, now, why is this important? Why are these, understanding what these potentials are important? And I want us to now do a thought experiment. If I put a piece of copper wire in a solution of silver nitrate, and I leave it standing at room temperature, I get a deposit of silver metal on the copper, okay? And and the copper metal dissolves in solution spontaneously at room temperature. I'll prove it to you now, we'll look at a video. If I do it the other way around, in other words, if I put a piece of silver metal in a copper sulfate solution, nothing happens, nothing at all. Why? It's got to do with the potentials. But before we answer the question, let's have a look at the video, which I think is very cool. Look at this. I think this is extremely interesting. And it's not working. Great. What is this? Alright. You know, in 1996, before all this crap Windows updates, things were faster. You know that? My 286 is faster than my current laptop. I tell you, I'm still going to have an aneurysm because of Windows. Okay, here we go. All right, now watch what happens. There is a nice a piece of copper metal, and we're now going to add silver nitrate to the solution. Well, at least I hope so. What is going on? Oh my goodness. Right. So he's added silver nitrates. Let's just look at it in miniature. AgNO3 silver nitrates going in. That's a piece of copper. It looks like a Christmas tree. Okay? Weihnachtsbaum. Now watch what happens. Look at that. The solution starts turning what color? What color is the solution turning?
Changing color?
It's turning blue, and look at what's happening. We're forming a Christmas tree. And this is, in fact, this happens spontaneously at room temperature. Isn't that amazing? Look at that. And that, all right, so let's stop this. What's going on here? We have a piece of copper. Let's write down the reaction. Actually, let's draw a schematic diagram of it. And then after that, we're going to take a break. So, here's our Christmas tree. This is copper. And I have silver nitrate, which is basically Ag+. Let's forget about the nitrates, it's a spectator ion. Now, what's actually happening? Well, we just saw. What's happening is the silver plus is being reduced to silver metal, and it's coating itself onto the Christmas tree, and the solution is turning blue. Why? Because the copper metal is being oxidized to copper 2+, and copper 2+ in aqueous solution is blue. So let's write down the half reactions. All right, that's the first half reaction. This is the second half reaction. Does everyone agree? That fits with the experimental observations. Silver plus, which is in solution, forms silver. Copper forms copper 2+. It forms a nice light blue solution. There we go. Now, is the reaction balanced? No. Multiply through by 2. Overall, the net reaction this is solid, of course. Right, that's the overall reaction. And now the question is, why did it occur spontaneously? I just put it in the beaker and I did it at room temperature. The reason why it occurred spontaneously is, in order to answer that question, we need to look at our table of electropotentials. So let's go back there. Here is our table. And so let's look at the half reactions. We've got copper going to form copper 2+, and silver going to form silver plus going to form silver. So, where are the half reactions? Here's the one half reaction. Copper 2+ plus 2 electrons forms copper, 0.34. So what is the potential associated with this half reaction as I've written it here? Minus, correct, very good. Minus 0.34 volts, because it's written in the opposite way. All right. So, copper 2+, just be careful. Be very careful, because there's another copper half reaction here. Don't fall into the trap. A lot of students pick this half reaction. That's forming copper 1 plus. This is the relevant half reaction. Right, and where's the other half reaction? Let's look. Silver. Here. Don't fall into the trap. Here it is. The second one is Ag2 plus. This is the half reaction. Ag plus an electron forms Ag. So what is the half reaction? And the potential associated with that is 0.80. Wait a minute. Yes, yes. So Ag plus an electron forms elemental silver 0.8. So what is the half reaction? What is the potential associated with this half reaction here? Plus 0.8, because it's written in the same way. No, it's okay. Well, it's difficult to see, but it's Ag plus an electron forms Ag 0.8. So tell me, what is the overall electrochemical potential associated with these two electrochemical events?
0.46.
Yes, we simply add them up. So 0.46 volts plus. Now, because we have a positive potential when we sum the potentials of the two half reactions, which we get from the table, and to invert the sign if needs be, depending on the direction of the reaction in our relevant half reaction, we get a plus value, so that means that the reaction is going to occur spontaneously. And we're going to get stuck into that in the second part of the lecture, but I just want to show you something else. By the way, the thought experiment we had in the beginning, we now know, and we saw we have experimental evidence for that, if we put copper in silver nitrate, the reaction proceeds. We get silver, we get the Christmas tree, and the solution turns blue. It occurs spontaneously because we end up with a positive potential. The second part of our thought experiment was, what if I put a piece of elemental silver in a copper sulfate solution? So a piece of, let's say that this is silver metal in a copper sulfate solution, so copper 2 plus. Will something happen?
No, because it's plus 0.34 and minus.
Correct. Because if I write down the half reactions, the expected half reactions there, it would be AgS goes to form Ag plus an electron, and copper 2 plus 2 electrons. It's basically the inverse, isn't it, of what I have here. And because it's the inverse, basically the signs are inverted. So it's going to be plus 0.34 minus 0.80, and if you add those two up, the result is negative. And so because the result is negative, because the sum of the two of the electrochemical potentials of these two half reactions is negative, the reaction is not going to proceed spontaneously. And that's the way to interpret this table. It's very valuable because you can predict whether or not a reaction occurs spontaneously or not. Just before the break, I want to just show you one further example of this, which I think is very interesting. Here we have the example of an iron nail put into a copper sulfate solution. This is also cool. So, you see, you can clearly see that it must be a high school teacher doing this, because no chemist wears a tie and a suit, right? This is just totally, that's the reason why I decided to work at a university, by the way. The thought of wearing a suit and tie every day is something I can't contemplate. He puts an iron nail in a copper sulfate solution, and look what happens. This is absolutely remarkable. Look at that. It immediately gets plated with copper, metal. So, during the break, I want you guys to just contemplate this. Think about what's happening here and why. And then after the break, let's take a nice 15-minute break so everyone can refresh. Let's reconvene at 22 for the second part of this very exciting exploration into redox reactions. But look at that. That's incredible. So you can actually tell your friends it's possible to dissolve copper. If they ask you, can you think of something where you can dissolve copper? You can tell them yes. You can dissolve copper in silver nitrate. It dissolves it. And you can dissolve an iron nail. Look at that. All right. See you guys in a moment. And we've still got quite. I think we'll manage.